Well, when I started writing these, by the way, I'll be giving all this on the blackboard and just putting figures up here. When I started writing these lectures, I thought this job would have been a whole lot easier 50 years ago to talk about early universe cosmology, because then there would be not so much to talk about. Big Bang, then Big Bang nucleosynthesis, and a few interesting epochs, matter radiation equality, recombination, structure formation. But now there's so much more to talk about because we know there wasn't really a Big Bang, and there was instead inflation, and before that, quantum gravity things, who knows. And now we have a whole list of particle physics cosmology topics to think about when we talk about early universe cosmology, and there's just not enough time to talk about all those in 5 days. So I'm just going to focus on inflation, on baryogenesis, and on dark matter, and even then it's a quite tall order, so I'll have to compress a lot. My goal is to try and give you some physical intuition and some references, and give you the big picture and show you where you can go for more information if you want to go deeper. And so obviously I'll be leaving a lot of things out. If at any point you feel I'm going too fast and it seems like, wait a minute, this just doesn't make sense, could you back up? Just please let me know, and I'll be happy to fill in anything that seemed to go too fast. Let me start with just a few preliminaries. First of all, units. We'll be using natural units for the particle physics, and for Planck's, for Newton's constant, I'm going to write something that might be a little different. So this is the unreduced Planck's constant, big MP, 1.22 times 10 to the 19 GeV. Or you can write it in terms of the reduced, 8 pi g. So, or you can write 8 pi g is 1 over the reduced m Planck. So that's just whatever over square root of 8 pi. And sometimes when you read papers, people use Planck's constant without telling you which one they're using. I'm always going to, I think I'll always be using reduced Planck's constant in these lectures. And furthermore, some people like to use capital M for reduced and little m for the big Planck mass. And I'm going to use this. And I was hoping we don't have to say too much about basics of Friedmann-Robertson-Walker cosmology. So I'm hoping that you all had some general relativity course where you talked about the FRW metric with the scale factor. And I don't know if this is the right metric signature or the wrong one, but the one I'm using is the mostly minus one. And then notions like I mentioned redshift.
D cubed x, is that a different notation for like for the 3x?
Yes, I'm glad you asked. So this is just the metric for three-dimensional space, which could be either flat or curved.
Okay. I guess normally it would is it like dx squared, dy squared, d squared, like.
Oh no, you're right. You're right. That's totally wrong.
The exponent was.
Why did I? No. You're totally right. It's. Thank you. Typo in my notes, and I suppose you might have noticed that my handwritten notes are linked on the wiki page. Yeah, and definition of redshift is basically 1 over the scale factor today divided by the scale factor at an earlier time. And, well, I guess it's worth mentioning the Friedman equation. So h squared, which Hubble parameter, that's a dot over a squared, is equal to, so in terms of this Planck mass, 3 over reduce Planck mass squared minus a curvature parameter over a squared. And sometimes we'll want to think of a as being a dimensionless number, other times as something with dimensions of length. So I'll try to be clear about when we want to do what. And I'll assume you know things like temperature, redshifts like 1 over a, and that the energy density of matter goes like 1 over a cubed, and the energy density of radiation goes like 1 over a to the 4th. So we don't have to, and things like the scale factor goes as t to the 1/2 during radiation domination, and t to the 2/3 during matter domination. Oh, and of course as an exponential, well, let's just call it e to the ht during vacuum energy domination, which will be important to us in this first lecture, which is about inflation. Did I say that? We're talking about inflation in this lecture. And I hope that we'll be able to maybe finish inflation sometime during next lecture and actually get on to baryogenesis tomorrow, so that we'll have enough time to give fair time to dark matter at the end. So, yeah, things would have been simple in 1950, but already back in 1979, shortly before I was a graduate student, things were starting to get interesting because an awareness was developing within the physics community that the standard Big Bang pictured had problems. And so probably you've heard of these problems as well. Actually, did I lose one of my boards here? No, there's still, but let's see, we won't cover that yet. I don't know what's the best way to use these boards, but going back to 1970, before I do that, let me just mention one other thing. What would be some useful references if you want to do some reading? And I know it's very dated, but I still like Kolb and Turner, Early Universe. And some things in there are obsolete, but a lot of the information is still quite useful. And then there was a book, a more recent book by Little and Life on, I forget the title now, but it was basically about CMB physics. And you can either find their textbook or there is a similar pedagogical review on the archive. Yes? Can you tell us what's out of date about Kolb? Well, how about over drinks tonight? And let's see. Oh, another thing that I like is the particle data group. They have lots of nice reviews, and these are guaranteed to be not out of date because they're updated every year or two. And so let's just talk a little bit of history. So back in 1979, people were starting to be aware, or an awareness was growing of the problems of Big Bang cosmology. And so first one is the horizon problem, which is that at some point along that timeline, there was recombination of protons and electrons into neutral hydrogen. Before that time, of course, photons were bouncing off the charged particles, scattering, not streaming freely, but after recombination at that redshift of, I think it was 3,000 or so, that's when the universe became neutral and photons could start streaming freely toward us observers. And so we're seeing the cosmic microwave background photons we're seeing are coming from the surface of last scattering at that distance corresponding to how far light could travel since the time of recombination. And of course, the light that we see from the CMB is extremely uniform, just tiny temperature fluctuations of order part in 10 to the fourth. And yet, if you think about it from the causal point of view, and you ask, how big was a region that was in causal contact with itself at the time of recombination, you can calculate that it was much smaller, as illustrated by these little circles. And so these regions that were in causal contact, we would expect them to be highly uniform in temperature, but not between two of them. And so we expect to see order 1 fluctuations in the temperature, or at least much bigger than part in 10 to the fourth, when we look out at the CMB, and yet it's extremely uniform. And to quantify that problem, you'd like to actually calculate, well, how big are these regions compared to the large circle? And so for that, one would like to introduce the concept of a particle horizon. And that's just how far could light travel by a certain time in the history of the universe. So you know that light follows a trajectory such that its line element vanishes. It's a null. It's a null distance in 4D space. So it's following a trajectory such that dt is ADX. And then you can, so remember, this x is a co-moving coordinate. The actual distance is blowing up with the expansion of the universe. If two observers are at a given separation in x, their actual distance is blowing up by a factor of a. And so the actual distance traveled by a photon in a given time is a times the distance it travels in co-moving space, which we calculate from here by integrating. So it's a times the integral dt over a. And then you can plug in how a behaves during matter or radiation domination to see that that is 2t in a radiation-dominated period, or 3 times the age of the universe during matter domination. Okay, so then what you'd like to do is just calculate the size. So the size of the little circle, the size of the little circle is the horizon distance at the time of recombination. And the size of the big circle is the horizon distance at the present time. So that's the small circle. This is the large circle. That's how big it is today. But of course, in this picture that we're drawing, we want to take it back to how big it would have been at the time of recombination. And so we have to divide by the amount of expansion. So that's the redshift at the time of recombination. That's the size of the big circle. So now we're comparing. Two length scales at the same time. So you just take the ratio of those two things, and you find that basically the big circle over the little one is a factor of 100, and then you can just do a simple calculation to figure out, well, what's the angular size of those little regions, and it's about 3.5 degrees. I don't want to waste too much time on the exact algebra. But so if you then convert that two-dimensional picture to three-dimensional, you see there's something like 10 to the fifth of those little regions that should be filling up our observable universe and making it look very inhomogeneous. So that was the horizon problem. The other problem was the flatness problem, and that relates to this curvature term in the Friedmann equation. So let's see. Here's the Friedmann equation. Oh, and let me just remind you how we rewrite this equation in terms of fractional energy density of the universe. And so if I rearrange the Friedmann equation by multiplying by 3m Planck squared, and I'll evaluate it today, that tells me the energy density today minus something that must have, here, let me call the scale factor R naught here, because now I want to think of it as being an actual physical distance. So that's the physical size of the current universe as we see it out to the surface of last scattering. And clearly this is something that also has units of energy density. And now if we divide both sides by, if I define this side to be something called the critical density.
Sorry,
yes.
R naught has no dimensions. Right? It's just, you just change A naught into R naught. Is that what you do?
Yeah, A naught is the same as R naught. I'm calling it R naught here to emphasize that now I'm thinking of it as a distance scale. Yes?
When you say size of the current universe, do you mean like we're still, the scale factor is not the actual size of the observable universe, because that's something that's complicated to measure, isn't it? The exact, because then you need to know the expansion history of the universe to know exactly the exact size of the observable universe.
Well, basically it's this size that we call 3,000 megaparsecs, which is...
It's a scale factor distance thing? It's a measure of the size of the scale factor? Or are we actually talking about the...
It's basically the horizon distance today. Yeah. Yes.
Sorry, how does the units work out in this equation? You have scale over a squared, so here A is dimensionless,
And then K would have to have dimensions. So.
So that's what you're reobserving to R.
Yeah. So now I'm going to think of K as being dimensionless. And yeah, so now if we divide both sides by, all sides by the critical density, then we have an equation that tells us that 1 is equal to the sum. And if we call these ratios omega, so then we have an equation that says 1 is equal to the sum of all the omegas, where the I stands for matter or radiation or vacuum energy. And we can define this thing to be, with the minus sign, we can define this thing to be an analogous curvature energy density. And so I just want to mention that because the experimental limit on this curvature density today, it's very small. It has to be less than about 0.015 in magnitude. So now if you think about, and so now we can plug this limit back into here, and I'm sorry. No, I take back what I said about R naught. R naught is a distance, and we're going to figure out how big it is here.
Okay.
Yeah. So R naught is just telling you about the physical curvature, and so if I plug into this limit, then I find out that R naught actually has to be bigger than the current horizon distance by a factor of 10. Okay, so and that's like 10 to the 27 meters or 30,000 megaparsecs. So the universe is extremely flat today. But now, if you think about running the clock backwards and figuring out, okay, what does that correspond to then at the Planck time, say? Well, then it just goes, it scales with the scale factor. So at the Planck time, we would say that the curvature of the universe is just equal to the curvature today, the curvature radius today, scaled by how much the scale factor has changed. And so that's going like the temperature today divided by the Planck temperature or the Planck mass. And so if we just plug in the numbers there, we find that this is an energy scale of 3 times 10 to the minus 3 electron volts in the denominator. Whereas the natural choice, if you go back to the Planck time, you should be at the Planck temperature, the Planck energy density, and the natural expectation is that it would be of order 1 over m Planck. And you see there's a big discrepancy there. It's saying that in order to explain the current universe, you would have had to tune the curvature at the Planck time to a small value, much smaller than its natural value by a factor of 10 to the minus 31. And so how do you explain such special initial conditions of the early universe? Why should it be so flat at early times? Well, around the same time, particle physicists were excited about grand unified theories. And everybody was thinking about guts. And you may know that one of the predictions of grand unified theories are magnetic monopoles, which are super heavy particles. And there was a paper by Klopov and Zeldovich where they tried to compute the relic density of these monopoles, and they found there would be way too many of them. They would overclose the universe. The universe would be way too dense compared to what we observe. And then John Preskill, he corrected their calculation because they didn't do it quite right. Around that time, Alan Guth was interested in the monopole problem. He was thinking about ways to try and get rid of the monopoles. And he wrote a paper with Henry Tai where they proposed one way to do it. But then he moved to SLAC, and he was doing his postdoc there, 9th year of postdocing, when he came up with another idea, and that was inflation. So that was his original motivation for inflation, but he quickly realized that not only did it get rid of the monopoles by just inflating them away, diluting them, but it solved these two problems at the same time. So let me just sketch what the picture was of inflation in his original paper. So he was thinking about this SU5 grand unified theory, and just like in the standard model where the Higgs boson breaks SU2 symmetry down, in guts you have some scalar field that's going to get a BEV and break the grand unified symmetry. And so you have a picture of the, well, now I'm wasting my efforts here. You have a picture of a potential which at very early times, because of finite temperature corrections that we'll talk about, it was just a parabola. It was symmetric around the having a minimum at the origin. But as the temperature goes down, then the finite temperature effects go away, and you start to see what the potential is going to look like at low temperatures. And at some point, you develop this bump that allows for tunneling of the field. Before the field tunnels, the universe is stuck in this false minimum that has a lot of vacuum energy. And this vacuum energy causes exponential expansion, so inflation. And then inflation is ended by the tunneling of the field, which then forms bubbles of the true vacuum. And these bubbles are supposed to eventually fill up the universe. Well, already in Guth's original paper, he realized there was a problem with this, because even though you get lots of inflation from this early period of expansion, the end result, these bubbles, turn out to be empty universes. And there are other problems. They turn out to be highly negatively curved universes. People didn't even realize it apparently at the time, unfortunately, you don't solve the problems that we just mentioned in this final stage. This was called old inflation. But it didn't take people very long to figure out how to solve that problem. Oh, and incidentally, so during this stage, we solved the Friedmann equation to find that the rate of expansion is going like this. So that was old inflation, but what people quickly realized was that if the potential isn't too steep once the thing tunnels out, then you can actually still get inflation during this part of the evolution, because the field can roll slowly enough so that that approximation, that equation, is still a decent approximation. And then it works. So now I'd like to give an outline of inflation.
I have a question going back to the horizon problems. You mentioned that you have something like 10 to the 5 small circles fitting in one big circle.
Yeah.
Is that connected to the fact that you observe anisotropies in the temperature power spectrum of 1 and 10 to 5?
No, that number is just a coincidence. Yeah. Yes.
You mentioned that the relative energy of the whole spectrum is mentioned in this whole sequence model. That somehow seems to like say that the zero energy of the real vacuum determines the absolute zero energy.
Absolute zero. Are you asking what determines absolute zero, or?
In other words, my question is that the V0 is the relative vacuum energy between the whole spectrum and the real vacuum.
Yes.
But that doesn't necessarily mean that is the vacuum energy which goes into the frequency.
I'm assuming that what's left over here is very small.
And how do you, that doesn't.
That's the cosmological constant problem. which nobody knows how to solve. Okay, so I'd like to give you a brief description of how this part works, which is known as slow roll inflation. And so we want the potential to be, in some sense, not too steep in order for this to work. In that picture, it doesn't look like it's very flat, but you'll see that the picture can be deceiving. So in order to quantify this, we introduce these slow roll parameters, which measure the flatness of the potential in Planck units, the relative flatness of the potential. So one thing you could consider is just the first derivative. And so this is v prime over v squared. And to make it dimensionless, one multiplies by Planck mass squared. And another one that's important, the same order of derivatives, is just the second derivative. And this is defined as m Planck squared v double prime over v. Now, these are called the potential slow roll parameters. And nowadays, people who do inflation for a living may prefer to use something called the Hubble slow roll parameters, which are defined to be a series starting with epsilon 1 is minus h dot over h squared, so the time derivative of the Hubble parameter. That turns out to be the same, approximately the same as the potential slow roll parameter epsilon. And then to generate the higher ones, they just take derivatives of the preceding ones. So epsilon 2 is epsilon 1 dot over h epsilon 1 to make it dimensionless. That turns out to be 4 epsilon minus 2 eta, and epsilon 3 would be epsilon 2 dot over h epsilon 2, etc. So if you read a paper by the Planck collaboration, they're going to be talking about these parameters, but I'm old-fashioned, so I grew up with the potential parameters. Now, how do these relate to the motion of the scalar field? So the scalar field equation of motion, well, in flat space, it would just be the Cline-Gordon equation. But in curved space, in Friedman, Roberts, and Walker universe, we have the square root of g, and so that's a cubed. And then we have g mu nu, that's the inverse of g, so that's a to the minus 2 phi dot squared in the Lagrangian. And I'm going to forget about spatial inhomogeneities, so then we just have the potential. And so when you vary that Lagrangian with respect to the fields, in addition to the usual Cline-Gordon kinetic term phi double dot, you get from the scale factor business, you get a Hubble damping term. So that's 3h phi dot is equal to minus v prime of phi. And again, this is ignoring spatial gradients of phi. So what happens in slow roll inflation is that the Hubble parameter is so large that this field is this term is negligible. And then we can just solve a simpler slow roll equation. And we'll see that that approximation is valid as long as these slow roll parameters are less than 1. So this is valid if epsilon and eta are, well, say much less than 1.
The bottom of the blackboard is not a good place to live.
You can't see, eh?
Go back here.
Okay, I'll try to avoid that. That one I cannot lift up. And so during that time, the field is evolving slowly, and the Hubble parameter is also evolving slowly. The Hubble parameter, it's getting very little of its contribution from the energy density from the kinetic motion of the field. It's mostly potential motion. And so you can integrate the Friedmann equation to get that the scale factor is going as e to the h integral of h dt. And we define this integral to be something that we call n, the number of e-foldings So that's the picture. That's how you evolve things during inflation. And then eventually, as you come down the potential, you're going to come to a point when one of the slow roll parameters gets big. So when epsilon or eta is of order 1, then we can no longer ignore the phi double dot term. In fact, the hierarchy reverses. Then we can ignore the Hubble damping, and we can just solve the usual Klein-Gordon equation. So then phi double dot is equal to minus v prime of phi. And usually at this point, it's just a harmonic oscillator. And so we just have a field which is oscillating, and that kind of field, that kind of configuration looks like cold dark matter in terms of its equation of state. So that's the end of inflation. And what has to happen is that through these oscillations, somehow the energy in these oscillations has to turn into radiation. So, for instance, if this particle, the inflaton, is coupled to standard model fields, then the oscillation of the inflaton is going to produce, well, the inflaton will just decay into those particles. So that's the simplest thing. So the inflaton decay causes reheating of the universe. And there's a very simple way to estimate how hot the universe will become. That's the reheating temperature, TRH. There's a very simple estimate you can make by comparing that to, or by knowing the decay rate of the inflaton. Because you can just say that reheating occurs at a time which is equal to 1 over the decay rate of the inflaton, and it's also equal to 1 over the Hubble rate, because that's the age of the universe. And so just by equating these things, since the so the Hubble rate is of order square root of energy density over the Planck mass. So that's of order m Planck over the temperature squared at reheating. And so now you can just solve this and estimate that the reheating temperature is of order square root of m Planck, and the decay rate of the inflaton. So that's a little bit surprising result, because you might think it should depend on the height of the potential, because after all, we started off inflation with all of this energy V naught, and somehow that should tell us how much energy is available for reheating. And well, that intuition is not entirely wrong. It's correct if the decay rate is sufficiently short. But if the decay rate is if the decay rate is slow, then a lot of the energy that's produced in these decays just gets redshifted away before reheating is finished. And incidentally, I put some exercises on the website. So one of the exercises on inflation is precisely about that question, and showing you how it's possible for V naught to divide out the final answer. Anyway, this is valid only if the reheat temperature is less than, that you calculate is less than the total available, what you would have expected as the total available energy. So now that's how inflation occurs. Let's just see how it solves the problems. And so one thing that's obvious is that the flatness problem gets solved just by the stretching of the just by the expansion of the universe, because any initial curvature is just going to get diluted by the expansion by a factor of e to the minus 2n. So that tells us how much inflation do we think we need in order to solve this 10 to the minus 31 tuning problem. So to get a factor of 10 to the 31 or minus 31 in the curvature, you can just solve this and find that you need n of order 70 e foldings. And well, that turns out to be a little bit of an overestimate, because in practice, if you look at the Friedman equation during inflation, including, suppose we had a positively curved universe, and if we included the curvature term in the Friedman equation, you would see that the initial curvature radius of the universe could not be too large, or you couldn't get inflation started because this curvature energy would be dominating over the potential energy. So that means that actually the initial curvature couldn't have been 1 over m Planck like I was thinking would be natural. It has to be somewhat less curved than that just for inflation to get started. And when you take that into account, you get a somewhat smaller number here. But that's not, I think, so in my notes I have that. You get about 65. So that's, that's flatness. And for the horizon.
Smaller does it have to be than the natural scale?
Oh, in order, let's see. That is a detailed question which people argue about who do numerical relativity simulations.
Small enough that it's not seen as still having fine-tuning in it?
is a matter of controversy. So some people like to say that inflation doesn't really solve the problem because you still needed some fine-tuning, but other people say, well, not really. You just need an accidentally, somewhat homogeneous place for it to get started, and then it takes over. You have.
You're saying you need less if you have positive curvature. What if you have negative curvature overall? What does that do to that number?
Then maybe it's not so important because then you'll still get expansion. But again, I think you would have to. In that case, then you would also worry, well, is the expansion then highly anisotropic? And do you ever really get a nice smooth patch that's blowing up homogeneously? So there is debate in the literature about this. I think there is more consensus that it's not a terribly worrisome problem. But people like Paul Steinhardt, who push for alternatives to inflation, often push on this as one of the weaknesses of inflation.
The other question I have is that normally when you see things, they're talking about the minimum number of equals of inflation that you've got for various models. The standard number is 46 to 60, and that seems to be from reheating temperature.
Yeah, I'll talk about how it depends on reheating.
This is so much higher than that 46 to 60 is interesting to me. Does that mean that this overrules that?
Well, let's see. So in my example here, I took 10 to the minus 3 M Planck, I think, as the initial scale, and then I got 65. 65 is not very far from the canonical maximal value. For the horizon problem, it's useful to think about a picture. I guess there's no pointer. Oh, there is a stick here. And this is a picture that basically appears in Colbin and Turner. And what it's showing you is how scales in the universe are increasing as a function of time, or parameterized by the logarithm of the scale factor. And what these green dotted lines are showing are some typical scales, which are just length scales that are expanding linearly with the expansion. So some co-moving scale that's getting stretched by the expansion. So this one is showing this is the size of the observable universe today, and it's just shrinking proportionally to A as you go back in time. And similarly, this is the horizon size at recombination. That was the size of the little circles in my picture. This is the size of a galaxy. And what we want to compare that to talk about these questions of causality, whether a region was ever in causal contact, is this particle horizon, which is of order the inverse Hubble parameter. And so that's the red line. It's showing how the inverse Hubble parameter is evolving as a function of time. And during inflation, the Hubble parameter was fairly constant. So it's just flat. But then inflation ends, and we get into Big Bang cosmology, where the scale factor, the Hubble parameter is going down like 1 over time, which is some power of, so A is t to the 1/2, so t is a squared, etc. And so what we're interested in is, say, the size of this little circle. So in standard Big Bang cosmology, where this line would just keep going forever, we would see that that size was never below the size it would need to be to have been in causal contact. That's the red line. But the good thing about inflation is that it cuts this off so that now these can meet, and now you can say, oh, there was a time in the past when that region was below the horizon, and therefore it had time to come into everything within it to be equilibrated. And so that tells us that as long as inflation lasted long enough, namely where these two lines intersect, then we've solved the horizon problem. And so then one can just do a calculation to figure out how long does that need to, let's see, how long does that need to be? Sorry, I have this one. Now I've confused myself again. I think I may have drawn this wrong. Oh, I'm sorry. No, yeah. I was saying the wrong thing. Yeah, we already knew that those things had been in causal contact. Those were the things that were supposed to be uniform within themselves. What we wanted was for a much bigger region to be in causal contact. That is the region containing those 10 to the 5 circles. That's this one. So this is the observable universe today, scaled back to earlier times. So that's why we want the intersection to be here. And now you can just do a little bit of trigonometry to compute how long, if you think about having a triangle along here, we can just compute this length versus this length and figure out how much of the bottom length had to be due to inflation in order to get this point to be here. So that's a calculation that, if you looked at my notes, is it's got a typo. So let me do that calculation. And that's saying delta log lambda over delta log A, that's the slope of the hypotenuse of that triangle. Well, that's just equal to 1 because the scales are growing linearly with A. But now if we look at the two sides, the change in the length scale was the horizon length at recombination down to the inverse scale of inflation. So at recombination, yeah, so we're looking at this point going down to here. And then we want to compare to this length. So this part is just the number of e-foldings. So that's the minimum number of e-foldings of inflation. And the part that's left over is just the logarithm of the scale factor at equality over the scale factor at reheating. I'm making a little bit of, I'm not distinguishing between equality and recombination here because it's not a huge factor. Anyway, if you look at my notes, you'll see something incorrect. It's saying that this is proportional to, or this is approximately equal to something. What it should say is that if I now solve this equation using standard values for the various quantities, I'll find that the number of e-foldings of inflation is going as the logarithm of the lambda I is the scale of inflation, so the energy scale of inflation. And that's just coming from the Hubble parameter during an inflation. And then we get some temperature scales at recombination and reheating. And that's actually a rough calculation. If you do it more exactly, you get something involving, so taking into account the difference between recombination and equality. It gives you some factors of order 1. And then this should be T equality over T reheating. But numerically, they're approximately the same. And so now we see what you were mentioning, the fact that there's some uncertainty in this number. How much inflation do you need depending on temperature of reheating, except this seems to be going the wrong way. For low reheat temperature, I should need less. I should need fewer e-foldings of inflation. For my estimate, I just assumed efficient reheating, so that the reheat temperature was of order the scale of inflation. And then, how should we do this? By the way, when is my nominal finish time? 1:15. That's accounting for your taking 10 minutes out of my? Okay. So I just assumed that the scale of inflation was of order the scale of temperature of reheating, and it turns out, we'll see, the maximum value you can use is around 10 to the 16 GeV, and the temperature of recombination is 0.1 EV. So then from this you find that you need about 60 orders of, or you need 60 e-foldings to solve the flatness problem. So it's interesting that that's a similar number to the one that we wanted for solving the horizon problem.
What motivated 10 to the 16 GeV?
This is the maximum. We'll see the maximum value that's consistent with observations, and this maximum value is going to come from the effect of gravity waves in the CMB. We'll come to that. So those were the problems that people wanted to solve, but it was also soon realized around 82 and 83 by Hawking, Starobinsky, Guth and P, Bardeen, Steinhardt, and Turner. And incidentally, that Bardeen, Steinhardt, Turner paper, I think that's the one from that era that's still really worth reading, that inflation solved one more really big problem, and that was the origin of density perturbations. And this is something that people had been worrying about because they knew how structure should form, how galaxies should form approximately, and that you needed a certain level of inhomogeneities in the universe, in fact, of order of part in 10 to the 4th, in order to explain the observed universe. So what we will see in the next lecture is that there are quantum fluctuations of the inflaton which are usually expressed in Fourier space. So let's take the Fourier transform of the space fluctuation in real space. And what we will see is that when the universe is expanding exponentially, one gets fluctuations which are dictated by the Hubble parameter. And so that's the size of them. And the other important feature of these is that, so this is a scale-dependent quantity. K is telling you it's the wave number corresponding to the wavelength of that fluctuation. On this side of the equation, we don't see any explicit K dependence. And H is roughly constant during inflation. So this leads to what is known as almost scale invariant perturbations. And that is also consistent with observations. So, a great kind of victory or indication that we're on the right track with inflation. So when would you like me to stop for coffee? Okay.
Lecture, we have 75-minute lectures,
Mm-hmm.
so people can ask you questions.
Yep.
I talked for a while, okay, and you just said, when I said we had to pick 15, you said, does that count your time? And I said, no. So I find a good place to put a period on the blackboard, and then we go get coffee.
Okay.
So
Okay, so I'll try to get through a little bit, just a little bit more then. So now, let me just try to give a picture of how these inflaton fluctuations give rise to observable, so for instance, the temperature variation in the microwave background. And here's a picture of the potential again, illustrating that you could imagine that different regions of the universe would have somewhat different values of the scalar field. And so it means that when reheating happens when one of these regions reaches the bottom of the potential and inflation is over, the other one is still continuing to inflate a little bit. And one of the consequences is that the spatial curvature in those regions is going to be a little bit different. One's going to get blown up a little bit more than the other. And so we're interested in the fluctuations of the spatial curvature, which is denoted by this script R at a given scale. So those will be given by variations in 1 over a squared. So we would like to know how much more the universe inflated in one region than in another. Well, of course, a is going like e to the ht. So this turns out to be h delta t, where delta t is the time difference between inflation in those two patches. And the time difference, that's just governed by the difference in field versus how fast it's rolling. And so we can, and we already estimated that this is of order h. So now we can plug in here, and we can see that this is going like h squared over phi dot. So now we have a prediction for how much the curvature is changing. And an interesting thing about this is, yes, it's almost scale invariant because these quantities are changing slowly during inflation, but it's not exactly. And the evolution of these quantities during inflation will give rise to a weak violation of the scale invariance, which is something that can be observed. And how do you observe it? Well, so this is, I can't write too far down on this board. So the observable, or something that's closer related to an observable quantity, is the power spectrum of this curvature fluctuation. It's known as the scalar power spectrum. It's related to the scalar inflaton. So it's the Fourier transform of the correlation function in real space of curvature at different points. And you can easily work out that, so this is what we call P sub S. You can easily work out that this is just the Fourier coefficient or Fourier amplitude that I denoted before squared. And so this is going as h to the fourth over phi dot squared. And by definition, people, can I still write here? People like to parameterize this as as an overall normalization, A, and a power law to denote the weak dependence on a scale that we're going to derive. Doesn't look weak, but so this is just a convention. NS equals 1 means scale invariant. And so what we'll see is that from slow roll inflation, we get a value of NS which is close to 1. And the small deviations are going to show up in the microwave background fluctuations that are shown here. So this is the first observation of the microwave background fluctuations by the Kobe experiment in 1992. And this is showing the correlations of temperature in real space. I'll just take 3 more minutes if that's okay. So this is looking at the correlation function of the relative fluctuations in temperature between different points in space. But since we're looking on the sky, this is in terms of angles instead of 3-dimensional space. And so this picture, it confirms an amplitude of order 10 to the minus 4 that people already knew you needed in order to explain galaxy formation. So the size of that was no surprise. And well, so these fluctuations are related to acoustic peaks, and they're more easily visualized in spherical harmonic space. If we expand the temperature fluctuations on the sky in terms of spherical harmonics, and then one can measure these coefficients ALM and define coefficients CL, which are averaging over the magnetic numbers. So for each ALM, you average over the M, and now plot these CL as a function of L, then you get a much prettier picture, also having oscillations. And these are the famous Doppler peaks or acoustic peaks. So I want to tell you what's the origin of those peaks. But the main point for what we're talking about in terms of the scale, the scale dependence of the power spectrum is that, well, it affects the details of these peaks, and so one can get a rather good measurement of n sub s, this power spectral index of 0.968 plus or minus 0.006. And this is from the Planck 2015 inflation paper 1502-02114. So I'll have to fill in more details in the next lecture. But I'll stop here and just take some questions if you... Yeah.
So what function we described the difference in the time that it takes them to roll down to the bottom, right?
Yeah, it's a very heuristic picture. You shouldn't take it too literally.
Yeah, so how much does this picture change? So the shape of the potential that you drew, you have to tunnel through the classical forbidden region before you can start tunneling down.
Well, that was in the original picture, but now we don't need the tunneling at all. We can just imagine that we started somewhere on the potential, and whatever happened before that's irrelevant.
I have two questions related to the scalar power spectrum. So just in terms of terminology, is that the same as the curvature power spectrum, or are those two different things?
Yes, that's the curvature power spectrum. And then we'll mention that the power spectrum for the density perturbation is related by some powers of k.
Okay, yeah. So the other thing I was going to ask is, I mean, really what you're observing is something more like the temperature correlations, and then you relate that to scale factor, and that in turn to curvature?
Well, there's a complicated story that I'm leaving out of how to, where did I put the, how do you relate this to the temperature perturbations? Because there's a lot of complicated evolution that goes on. You need to compute a transfer function. You need to do evolution. You need to solve Boltzmann equations. So, it's a, well, I guess it's a linear relation, but it's a complicated functional relation that's relating those two things. And for those details, the book by Little and Leith is a very good place. Okay, I guess we can have coffee then. Oh, there was another.